So let's do so for yesterday what we did, when the charged particle enters the magnetic field perpendicularly, right?
Yes, sir.
So today we will do when the charged particle enters the magnetic field at certain angle. So today maybe we call this as case 2, when the charged particle enter the magnetic field at an angle theta. So let me draw this diagram now. Imagine this is a charged particle which is entering a region of magnetic field. The direction of the magnetic field is this way. Yeah, like this. This is the direction of B. Now, this being the velocity vector, you see it is entering the magnetic field at an angle theta. So this being theta. Okay. Now what we can do is that we can imagine we can resolve it into two components. One will be V parallel component, which is the one which is parallel to the magnetic field, and another will be the perpendicular component, which is perpendicular to the magnetic field. Now what will happen is that the parallel component, the perpendicular component, will try to make the particle move in a circle. Okay, the perpendicular component will make the particle go in a circle,
Circular motion.
In a circle like this, about this axis. But the parallel component is also there. So the parallel component will try to take it in the forward direction. And as a result, its path will be a helical path. So charged particle is going to move in a helical path about the axis. Okay? So something like this way. So this is the charged particle going like this. Okay, so let us see this in action. So we can say like this, that let a charged particle plus Q enters a magnetic field B at an angle theta to the direction of E, to the direction of B vector. Okay, to the direction of B. The velocity, let us charge particle plus Q enter the magnetic field at an angle theta to the direction of V with the velocity V, vector. The velocity V vector. The velocity V can be resolved two components, that is V cos theta, V perpendicular, V sin theta. Okay, V parallel component is V cos theta, and V perpendicular is the V sin theta component. Okay, V perpendicular component being perpendicular to B magnetic field provides B perpendicular magnetic field, okay, due to perpendicular component due to B perpendicular component being perpendicular to B vector, the charge particle experience the necessary Lorentz magnetic force, experience the Lorentz magnetic force. Fm is equals to BQV, right, sine theta. But here you can see V perpendicular is perpendicular to magnetic field, so this theta and this theta is different, okay. So this is different. Let me name this theta 1. Here theta 1 perpendicular and this is 90, so this would be BQV. Under this force, the particle follows a circular path. Okay. So if this is x, y, z, it will be following in the so follow the circular path, right? Now it follows the circular path in xz plane. Can you see the xz plane? It follows circular path in xz plane, right? Means I'm talking about this plane. It follows circular path in this plane. Also, due to V parallel component, the particle also moves parallel to B. The end result is that the particle follows a helical path through B, through magnetic field. Okay. Hence now the equation will be, so now you see the necessary centripetal force is provided by mv perpendicular square by r is equal to bqv, right? V perpendicular, this is perpendicular. So in this case r will be, then these things get cancelled one, so I get here r will be mv perpendicular by bq. So this is the now radius. That means I can write this as also like this way: r is equal to mv sine theta by bq. The theta is the angle at which the particle has entered the magnetic field. Okay. Now we can also find something called pitch. What is the pitch? So in okay, we can come to the pitch also. So before that, we have found R. What else can we found? What else we have found in the last class? We have found out the time period also. V velocity also we have found. So V will be, in this case, from this equation we can easily find time period, right? So we can write this way also. We can write 2 pi r by t. So time period can be written as 2 pi now you can see how I'm writing this. This is another way of doing it. You see, we know omega equals to 2 pi by t, right?
Yes, sir.
And then what you can do is we can write omega as v equals to r omega. So omega can be written as v by r. So v by r is equal to 2 pi by t. Then t will be equal to 2 pi r by v. Can I write it like this? This is the v perpendicular one. Okay, so then I can write 2 pi into r is how much? R is mv perpendicular, right?
Yes, sir.
By bq into v perpendicular, right?
Perpendicular, yes, sir.
So then what you see is that mv perpendicular, so vb get cancelled. I'm left with 2 pi m by bq. Isn't this the same time period or not?
Yes,
So
sir.
the time period is same. It is again independent of the velocity of the charged particle. It only depends on, note, you note thing the more important thing to note. Time period is independent of the charge velocity. It is not present in the equation. Yesterday also you see it is not there, right?
Of charge velocity.
Yeah, velocity or independent of the charge velocity or velocity of the charge, whatever, which sentence suits you better. Okay, now this is it. Now we can also find something called the pitch. So what is
Pardon,
pitch?
sir?
Pitch, P-I-T-C-H, pitch.
Pitch.
So pitch is the linear distance travel in one complete time period. So what is time period? Time period is the time taken to complete one revolution. So pitch would be linear distance traveled by the in time interval, right? In time period t. Right or not? So what do you think will be linear distance? So this is called the pitch. So linear distance travel will be how much? So you see the distance travel will be depend on what? So pitch we can easily find out by pitch will be, that is into pitch is actually that pitch is the distance. Sorry, what I'm distance or what I'm writing. No, this is not the expression for pitch. Sorry, yeah, this is expression, but that is for the in case of instruments. But normally pitch will be, we know that pitch would be the v parallel component into time. With this velocity, how much distance will you cover in a time? So v parallel would be v cos theta into t. Now what is t? T is the same, only 2 pi m by bq. So pitch, that is x, will be, that means the distance traveled in one time period, one revolution. Okay, in one revolution, the linear distance traveled, because it is moving in a helical path. Okay, so x would be equals to v cos theta into t. T will give me 2 pi m by bq. Okay, so x is equal to, now you can see this is v. This is what v? This is the velocity with which it enters. Correct? If this one depends on velocity. Yeah, definitely. But time period, remember this is a 1 mark question or tricky question. This is a knowledge based question, so I'm highlighting it. Is that it is independent of what? It is independent of the time period is independent of velocity. Okay. So let us see one example. Come on, right in here. Mhm.
Mm.
Let's see. Yeah. So you can clearly see this. The author is the attribute to Tom Waltz. Okay, the author is Tom Waltz. So now what he has done,
Just everything according to particle path. Ooh.
is it clear?
Yes,
Increasing the charge increases. If the charge increases, frequency, charge increases, time period reduces, right? Yeah. And what on to the path? Radius. If charge decreases, R also, charge increases, R decreases. So I'm increasing to 6.4, 6.57, radius of the circular path is decreasing,
decreasing.
right? We can control many things. Mass increases, mass falls, time period is increasing. Okay?
Decreases.
Right?
Time. Yes, sir.
Interesting, no.
Yes.
Now show the magnetic field. This is the magnetic field. So the velocity vector, this is the velocity vector. It is perpendicular, it is always tangent to that surface, no?
Tangential.
So very good, very good work by this. The author has done
Yes,
very
sir.
good work, no?
Yes, sir. Very nice.
So we can see this in 3D also. This is the 3D explanation, reset. So this is, let me play it. Here it is going. Now you cannot move it. Okay? Nice, no? Now if you look on the top, the one which is shown in the book, it looks like a circle.
Okay.
It looks like a circle. If you're looking on the top, this is what you have seen. Please let me hold on. Let me
Yes,
pause
sir.
it. Look at the direction. Does it allow the force? The force is inside, no? Check.
Yes, sir.
Check the law. That what is the direction of the Lorentz force? So velocity is this black arrow, and magnetic field is coming up. So that means what? What does this mean?
So, isn't opposite.
So use the what is the direction of the force? Use your right hand rule to say. So my right hand aligned with the black arrow, and magnetic field is up. Yeah, you can see. I'm showing you with my hand. You can check here. You see, I'm showing it is like this. So I have to fold it towards B. B is coming up, so is inside. Okay, just try a little bit. You will understand. You have to align your right hand with here.
So,
And then,
along the direction of the black arrow, no, sir?
yes, you have to
So that
align your hand.
If we align it, won't the direction be downwards?
No.
Since the arrow is outwards,
No,
so
no,
you
no.
keep it
Force will be always inside the center of this, towards the center of the circle. towards the center of the circle. Okay?
Yes.
So I hope you've got the picture, right?
Yes.
Explore more. GeoGebra is a very classic, great tool. Explore more. So very soon I'm going to put my own resources there. So let's see now. Now we'll come to the next topic, cyclotron. So what is a cyclotron? Or before going to cyclotron, let's take one question. An electron enters a magnetic field with a velocity v equals to 4 into 10 to the power 4 meter per second. Electron enters a magnetic field with a velocity perpendicular enters a magnetic field with a velocity horizontally. Let me write that. Electron enters a magnetic field horizontally with a velocity of 4 into 10 to the power 4 meter per second in a region where B acts downwards okay, if the strength of B is 10 to the power minus 5 Tesla, draw the trajectory of the charged particle. So you have to draw the trajectory. What is its radius? So that means this has been given to you. This is the magnetic field. Okay? We need to find its radius. Okay? Let us find the radius first and then see. So now horizontally, let's say the charged particle is entering like this. So what will happen? I have already taught you this. So we know mv square by r is equals to bqv. Okay, v weight cancel. So r will be mv by bq. So it is charge of an electron. So 9.1 into 10 to the power minus 31 into velocity is how much? 4 into 10 to the power 4 divided by magnetic field is 10 to the power minus 5 Tesla into 1.6 into the power minus 19. So then how much is it? So 31. 5 and 4 is 9. And 31 minus 19 will be 31. So it is like this, na? 9.1 into 4 into 10 to the power 30 minus 31 into 10 to the power 19 into 10 to the power 9, because 5 plus 9 divided by 1.6. So 31 and 20. If I subtract 31 and 20, I get here how much? 11. So 11. So it get, no, not 11. It would be 12. No?
So 11. 31 and 20.
12. It would be 12. So 9.1 into 4 into 10 to the power 12 minus 12 divided by 1.6. Okay?
So 31 minus 20?
No, 19. I have done with the 20, no? Is easy. So
Uh-huh.
31 minus 20 will give me 11, but it was 19, so 1, that gives me 12. Okay, so then 9.1 into 4 and by 1.6, so this get out, and I get anything else is missing. Okay, into 10 to the power 9 is also there, so that gives me 10 to the power minus 3. So 91 into 4 divided by 16, around, divided by 16, sorry, what I'm doing 91 into 4 divided by 16, around 22.75 into 10 to the power minus 3. Okay, so 5, around this much, 22, around, we can keep it like this, 22.75 millimeter. Okay, or yeah, let us keep it like this, 22.75 millimeter, right? So now what is the direction of this force? So we see this is the velocity vector, the force is going inside, the magnetic field is going into the board, into the paper. As it's going into the paper, that means I have to align my V with V, so you can imagine like this way, this is V and this is B. Oh, sorry, no, not this, little bit of, and the cross means going into the board. Imagine you are taking a pen towards the board, okay, or towards the plane of the paper, and one more plane on the, from left to right towards east. So now align your hand, right hand on the velocity vector, and fold it towards the which side the charged particle will take the turn?
From left to right. Right. So, go inside.
Okay, so what do you think? It is going in which way?
Yes, sir, inside.
But it is an electron. Don't forget, it's an electron. It's an electron, negative charge. We'll see this later. It's a negative charge, but it's a negative charge. So charged particle will turn in which way? So it's V cross B. So V cross B will be, if I this is the V vector, fold it toward the B vector. So this one should be going. Now better if you can understand this with the help of how can I say, I think this question would have been done better if I do with the Fleming's left hand rule, because you see charged particle is associated with a current, motion of charged particle is associated with a current. Okay, we'll talk about that very soon. Right now you know that the charged particle will be coming out like this way. Just a minute, I think I have given the question right now. It doesn't matter if you horizontally with a velocity. Yeah, cross product. So cross product V cross B is V cross B. So V cross B is V cross B. Yeah, it is. You see, look, what is the force experience? Yeah, I have given the question right only. Nothing mistaken here. You see, force experience would be what? Q V vector cross B vector. Right? What is Q here? Q is an electron. So it should be minus E V vector cross B vector. Minus is there, no? So that means what? The force is negative. So if I take the right hand, okay, it's a very fine concept here, you see. If I take the right hand, align it with the velocity vector and fold it toward the magnetic field, then the force is coming this way, right? But it is what? It is what? For an electron, if this was a positive charge, it would have went that side. If this was a positive charge, it would have went this way.
Yes, sir.
But it is being electron. Same force but negative direction. So that means so it will be
downwards.
So that means the electron will be entering. This is what I was trying to explain you in yesterday's one. This will get more clear when we use Fleming's left hand rule. It will get more and more clear in this. So you see, this is how it will come out. And this radius from here to here, this radius is 22.75 millimeter. 22.75 millimeter. This is radius. It will enter and come out. Got it?
Yes, sir.
So I hope you will remember why this is negative. If this was positive, it would have went that side. If this was instead of electron, if this was a plus Q, it would have went that left hand side. Okay? But if it is negative, so it will be coming this side. Right? Now let's continue to cyclotron. Let's come to cyclotron. May I clean it?
Yes, sir.
So cyclotron. Cyclotron. What is a cyclotron? Cyclotron is device. It is a particle accelerator. It is a particle accelerator. It is simple way you can say that. It is a particle accelerator. Okay. It can accelerate charged particles like alpha particle, like protons, okay, then some like that, but not electron. Got it? But it cannot do alpha particle.
Like alpha particle?
Alpha particle, protons, okay, a positive charge, other subatomic particles, but not electron. Okay. So now, alpha particle, proton, then many other. I'm forgetting the names, etc. But not electron. Okay, but not electron. We'll see that. To accelerate electron, special cyclotron known as synchrocyclotron. Synchrocyclotron is to accelerate electron. Special cyclotron, no, synchrocyclotron is used. Okay. Now it works on the principle. What is the principle? It works on the principle of Lorentz force. That is a moving charge in a magnetic field experiences a force in what kind of force? Not just every kind of force. It experiences a force in a direction perpendicular to the
Lorentz force.
Lorentz force, that is A moving charge in a magnetic field experiences a force in a direction perpendicular to the plane of velocity and magnetic field. So what does a cyclotron consist of? So how does a cyclotron look like? You see, a cyclotron will have two metal. I'm going to draw two diagrams here, one to explain you and another to the one which you will draw in the exam purpose. So these are, cyclotron has two now whatever I'm saying, no, you can use it to, as these things will be recorded, you can use it later to make the notes from here. I'm not going into detail, okay? So cyclotron consists of two D-shape containers. Is a D-shaped container, as you can see. D-shaped containers. These D-shaped containers are connected to a very high frequency oscillator, that is AC frequency oscillator, which makes this time, sometime it makes it positive and next time it makes it negative. Also, the whole arrangement is placed in a evacuated chamber and inside a magnetic field, a region of magnetic field. So magnetic field is present perpendicular, either from up to down or down, top to down. For example, this is the direction of magnetic field. So this is how magnetic field is going, like this. Okay? This is how magnetic field is going. Magnetic field is directed perpendicularly downward. Maybe there are two pole pieces. Okay?
Yes, sir.
So you can see these are magnetic fields like this. So the container is hollow from inside, as we have said. The container is hollow from inside. And these two are connected to, these two D-shaped containers are connected to a very high frequency AC source. The AC, if you remember, it has a positive cycle and a negative cycle. High frequency means it is like this. Okay? Very high frequency means within few seconds its polarity changes. Okay? We will talk about this. What is this frequency? Will come to this is called the cyclotron frequency. We'll come to that. Now what happens is that when we release a charged particle, plus Q here from the source. Now before I carry on the mechanism, one more thing I must say here is that the whole system is placed in an evacuated chamber. Okay, and there is a small opening. We call this opening as a window. This small opening. I should also draw the top view of it. So the top view will look like something like this. The one which you have to draw mostly in the exam when it comes for you to draw. So it will have a D shape here. This is a D shape as you look from the top. Okay, there is a small opening. This is the window which you are not seeing in this picture, but it is there. Maybe I can show you in like this way. Here is the window. Okay, here we collect it. From here we collect the charged particle. This is how these two are connected to a very strong frequency or strong oscillator, high frequency oscillator. The whole system is kept under a magnetic field which is perpendicular to the and this whole thing is present in an evacuated chamber. Okay, it's kept in an evacuated chamber. Now when we place a small test charge here, let's say plus q, the plus q, and at that moment the, let me name this as d1, let me name this as d1, this is d2. Now when we place the plus q at the source, this is the source, d1 being negative, so I am making d1 negative and d2 positive. So d1 being negative, it will get what? So there is what, as try to notice there one thing, as this side is there is a positive and negative voltage in between the plates, in between the two Ds. That means there exists an electric field, right? There exists an electric field between these
Two plates.
two Ds, not plates, Ds.
These,
Now the direction of these switches, so I am giving it two arrows here. That means sometime it will, because it's oscillating now, the polarities of the two Ds is going to oscillate. So as the polarities of two Ds oscillate, so what will happen? So polarity of two Ds oscillate, then what will happen is that sometime D1 will become positive and D2 will become negative. So electric field also switches, right? So now here also I can see the same thing here. This is the polarity here, like this. Okay. Got it? Now when this plus charge, plus q is placed there, it under the influence of this negative potential, it will get accelerated. It will get accelerated. It will get accelerated. How can it get accelerated? Because we know that electric field is given as force per unit charge, and
yes,
then
sir.
force can be written as mass into acceleration by charge. So acceleration would be QE by m. So the charged particle is going to get accelerated by this amount in this gap, and it enters the D1. As it enters the D1, you see it is entering the D1 perpendicularly. So V, so you can, V vector is downward and V vector is straight. That means V cross B. So that means now as soon as it enters, the purpose of the magnetic field is to give it a circular path, right? Turn it. So with the same velocity, without any loss in velocity, because time period is independent of velocity, right? So it brings back to this point. Okay?
Yes.
Got it?
Yes, sir.
So you can also note here that it works on the principle of Lorentz force, and also this include it with that it works on the principle of Lorentz force, that is moving charge in a magnetic field experiences a force in a direction perpendicular plane of the velocity and magnetic field, and the frequency of time period, the frequency and time period,
And
I'm writing, and the frequency or frequency
and time period.
or time period, yeah, same thing, frequency and time period, you can say any one of them. Frequency of, just write frequency, and the frequency of this motion is independent, is independent of the speed of the particle. Okay?
Yes.
Independent of speed of the particle. So it enters there. Now come back. So the charged particle enters the magnetic field. As it enters the magnetic field, it gets a circular trajectory, right? And comes out with the same velocity. By the time it comes out, okay, in time t, the polarity switches. Earlier it was negative and this was plus. Now this one will become negative, this one become plus. So the particle will get what? Accelerated now. It will get accelerated only within the gap. So now its velocity again increases. As its velocity increases, it again enters the d2 perpendicularly. As it enters the d2, now it covers a circular path of greater radius and comes out near the end of d2, near the, after taking a turn again at the entering position, it again comes out, but in a greater radius, correct, in time that same t only. Got it? And then again by that time the polarity switches. So these become negative, now this becomes positive. Again it will get accelerated in between the gap, gets into the d1 again, and again it spins. Now this time it's going to go for a even more greater path, right? Same process continues here. Same process continues here. It will go on and on like this, right? Goes on and on like this way. At certain point we want it to collect it and use it in the nuclear reactions for bombarding with some other element of thing. Okay, so at that time we'll open the window and we'll collect it from here. This will go towards a nuclear reaction. This is how accelerator works. So I can draw it here now. So like this. Okay. At certain point, what happened? The velocity of the,
does it come out or
we collect it? Yeah, it come out. There will be one tunnel through which it will go. Particle accelerator. This is the principle. Okay. So you can draw a little bit properly. Now at one certain point, what happen? The velocity will become so large that the radius of the circular path become equal to the diameter of equal to the what do you call, the d's. At that time you cannot hold it anymore. It becomes so large. So at that time what will happen? You have to collect it through the window. Okay, you have to collect it through the window. Remember. Now you may ask one question here: what will happen, sir, if the electric field is not present within the gap? Will it still accelerate? Will it still function? Yeah, it will function, but that time then it will move only in a one circle, one continuous circular path. Okay, so it may happen that you have accelerated the charged particle, and you don't want to collect it. You want it to stay there only with that constant velocity. Okay, so in that case what will happen? I will stop the electric field. I'll switch off the electric field. See, the electric field switch off is not going to accelerate because acceleration only takes place within the gap. So this is one application based question, that in the cyclotron, if the electric field between the gap is closed, what do you expect? What do you expect will happen then? So you will say at that time the electron, the charged particle will follow a constant circular path.
Constant circular path.
Just for circle, it will keep spinning and spinning and spinning, as if it has been now maintained there. But magnetic field should not be closed. So within the D, it will move at a constant radius, and it will keep moving in that. As soon as I want to again collect it, I will bring in the electric field. Okay, and as the electric field is turned on, it will again get accelerated, and then I can collect it from the window. That's it. So it is like a jar, no, where we can keep it charged particles. Clear? So this is the cyclotron. So how to write the answer for cyclotron? So for cyclotron, it works with the principle of Lorentz force. There is a moving charge particle in a magnetic field exerts a force direction perpendicular plane. Okay, and the frequency of this motion in the magnetic field is independent of the speed of the particle. Okay, frequency, or you can say, if you don't remember the frequency, you can say time period of this motions is independent of the speed of the particle. Correct? So again, the same derivation will carry out. Same derivation we can carry out. So that means we can write. So you see, magnetic force provides the necessary centripetal force. That is, this is the principle. mv square by r is equals to bqv, not r square. Sorry, bqv. So v get cancelled. I get here again r is equals to mv by bq. Got it? Then I can find out again time period, which I have already taught you how to do it. So time period will come as 2 pi m by bq. Same way. 2 pi m by bq. You see, time period is not present, right? And the frequency will be given as frequency nu would be equals to 1 by t. That gives me bq by 2 pi m. 2 pi m, right?
Yes, sir.
So this is the m. 2 pi bq by 2 pi m. Okay, what is the kinetic energy of the, this also we have done. So kinetic energy of this electron, or maximum kinetic energy, will be what? Again, we can find out maximum kinetic energy. We can easily find out, velocity. From this expression, velocity is how much? V is equals to bqr by m. So kinetic energy would be a half mv square, right? So half m bq, half m v square. So bq b square q square r square by m square. So 1m get cancelled. It is b square q square by v square by 2m. This is the kinetic energy of the, what? Of the maximum kinetic energy of the accelerated charge particle in the cyclotron. Okay, so we can see a cyclotron here also in.
So what?
Oh, sorry. Yes.
Yes. So no, I was just copying someone. Yes, it does.
Now, so this is. So this frequency, don't forget that it's called the cyclotron frequency. Please write it here, or else I'll forget to tell you. This is called the cyclotron frequency. Okay? May I clean it?
Yes, sir.
Sure, now I'll clean it. Okay, wait. Before that, let us see one resource from here. Cyclotron. Let us see one cyclotron here. Okay, cyclotron is not there. Okay, I will show you real life scenario of a cyclotron. What is a cyclotron? There are now particular a large hadron collider is there. Cyclotron. Here is your cyclotron. Let us look at the Wikipedia as it is in the nothing else. Okay, only with the Wikipedia. Sorry, yeah, this is wiki. So in the wiki you see this is the cyclotron. Can you see this tunnel?
Yes, sir.
From here it is collected. That window.
Oh.
Okay, and this is the modern one. Okay, that shaft. This is no. Here is the. Okay, so here these are just look at this fine diagram here.
Yes.
So can you see this is the actual picture? This is the first schematic sketch, na? You see this is the oscillating frequency. Two metal insulated from each other. This is the one path. You can draw this diagram also. Top view of the disk. Okay, so here you can see the charged particle is spinning there in a spiral path. Okay, this is also section of the disk. Very well schematic here. You see this is the arrow that are giving you the magnetic field. Okay, and these two, you see, these are magnetic coils. So if you go back, can you identify them? What are these two? These two are magnetic coils. These are magnetic coils, right?
Magnetic coils.
So that provides the very strong magnetic field.
Uh-huh.
Here is another picture of it.
Okay.
You can now find out from here what are different.
So what are these that are connected?
So this is vacuum chamber of this is the vacuum chamber of Lorentz, 69 centimeter, 932 cyclotron with cover removed. This is the cover. This is a vacuum chamber. The cover has been removed from here. Okay. Now here is the another one, high frequency oscillator. Yeah, this is it. Please identify different paths. Identify the different paths where which part is what. Which is the first, I think the first working stage of French cyclotron produced in Zurich, Switzerland in 1937. The vacuum chamber containing the D's at the left. D's at the left has been removed from the magnet. Yeah. So this has been removed, taken away from the magnet. Okay, to show you actually how does it work. And then I think this is Lorentz 60-inch cyclotron showing the beam of accelerated ions. Can you see the accelerated ions?
Where's the cyclotron, sir?
This is the cyclotron.
So, but it's D-shaped, no?
No, you are looking for one particular angle. You are looking through a particular angle. This is the cyclotron. These two top points are the source of magnetic field. Look, no, that beam, that blue color beam you see,
Okay.
Oh no, this is exiting the machine.
I think, sir,
It's exiting the machine. It is coming out. It is coming out, exiting the machine and ionizing the surrounding air, causing a blue glow. It is coming out.
Okay.
Got it? So
Yes, sir.
this is that actually.
Yes, this one is that.
Correct. So it is M. Stanley Livingstone and Ernest O. Lawrence, right, in the form of Lorentz 69 centimeter 27 cyclotron at the Lorentz Radiation Laboratory. The carved metal frame is the magnet core, U shape. Okay. The large cylindrical boxes contain coils of wire that generate the magnetic field. So these are the large boxes. Just few minutes back we have discovered. I've told you, no, that these are the two main source of magnetic coils. Okay, understand what is cyclotron?
Yes, sir.
So make up the notes on the cyclotron, how to do it. I think this is enough for you. Now limitations of cyclotron. The cyclotron is limitation. First of all, limitations. May I clean it?
Yes, sir.
So limitations of cyclotron, I've already told you the most important one. It cannot accelerate electron. It cannot accelerate electron.
I cannot accelerate.
Electron. Why? Because of its so less mass. Because little increase in their energy, in their energy correspond to correspond to large increase in the velocity of the to a great extent, or you can just say it cannot accelerate electron because a little increase in their energy, that means little increase in the kinetic energy corresponds to a large increase in their velocity. Okay,
In the velocity.
yeah, large increase in their velocity. This is due to the small mass. And second thing is that you cannot accelerate neutrons. Neutrons cannot be accelerated. Cannot be, because they are electrically neutral. Because they are electrically neutral. Done. Okay. Now, one more is there, that according to Einstein's relation, according to Einstein's special theory of relativity, that is the mass of any particle is given as m naught by root over 1 minus v square by c square, where m naught is called the rest mass of the particle. Okay, rest mass of the particle. So at high frequency, what will happen is that at high frequency, at high velocity, the frequency of the cyclotron, at high velocity, the frequency of the cyclotron will decrease. Frequency of cyclotron will decrease.
Velocity.
Frequency of cyclotron will decrease, and this is due to resonance. Will decrease due to, first you write, due to increase in mass. Okay, because you can see, tell me the equation of frequency. Frequency is most probably bq by 2 pi m, no? bq by 2 pi m. So if mass is very large, frequency should decrease. If mass increases, frequency should fall. Yeah, so cyclotron frequency should decrease, right? Right? This will throw the particle. This will throw the particle. This will throw the particle out of resonance. Out of resonance. Resonance with the fields, with the oscillating field. With the oscillating which field? Electric field. Oscillate with the oscillating electric field. Okay, these are the three disadvantages of limitations of. So I have given you the first two things which you can remember easily. First one, it cannot accelerate electron because little increase in velocity will give rise to huge amount of energy to the electron, and you won't be able to. Little bit of increase in energy will give rise to huge amount of velocity. Okay, and that becomes so unstable in the cyclotron. And secondly, neutrons you cannot. Okay, so these are the common drawbacks of cyclotron. Clear?
That's it.
That's it.
Like only these are the limitations.
That is the limitations of cyclotron. Okay. So